Oops. And it works. Yeah. And I prepared for you again a wonderful menu of chemistry items. Okay, I'm sure you will enjoy. The title is nothing less than limited reagents. Okay, but before I do that, I'm gonna dive into some of what we talked about last time. That was the last item, and that was basically if you have a chemical reaction and you're given a certain amount of the starting material, you can calculate how many grams of the product you generate. Okay, so there's a couple of conversions there, and we're going to come back to that right now. The basics of this is all, I have to put this picture up, it's all counting. This is all about counting numbers of molecules and compounds. Right? This is how many do you have of something. And we make conversion between grams, which is a mass, to countable objects, which we happen to express in moles. Moles is just a convenient quantity for expressing the number of molecules in it. Okay? So that's how we use the mole. Now, this is a question that we had last time. We solved it, okay? And the way we did this, the very last slide, just to remind you, we started with the starting material. We had 100 grams. We made a conversion from grams to moles because moles is a quantity, a countable object. Now I can actually compare two quantities with one another. I cannot compare two masses with one another because every molecule has its own mass. That's the same as I say that if I deal with you guys, all right, you guys have all different kinds of masses. So a mass of your neighbor may not be the same as your own mass. So dealing with comparing masses doesn't necessarily tell me anything about how many people are in this audience. Right? If I want to do that, I have to go away from mass and go to a countable identity, which is a human being. I can count that. Right? The mass of a human being is not necessarily important in that regard. So I'm going from mass to quantifiable, countable object, which is mole, and then I can relate one quantity to another quantity. The quantity of starting material relative to the amount of the product. The ratio is 1 to 1. That's what the chemical equation says. For each 1 mole of this, you generate 1 mole of the other. And then you go from moles, which you now have. The product is now expressed in moles. I want to express the product in grams again, and I make this conversion. From grams to moles, mole ratio, and then from moles to grams. And we found the answer. Same answer last time, of course, 72.3 grams. And this holds for any kind of chemical equation. So that means it also holds for this one. Yes, question. Say again? This is the molar mass of this compound. How do you get that? You go to the periodic table, 2 times chlorine, and then you add it all up. Okay? Okay, so let's quickly do this for another question and see if we get this. Okay, so this has solid zinc reacts with hydrochloric acid. That's here, those are the reactants. And they produce 2 products, namely zinc chloride and hydrogen gas, right there. The question is, what mass of zinc chloride, this product, do you form if you have 1.528 grams of solid zinc? Okay? And we assume then that this is an excess. So this is not a limiting factor that we're calculating. There's enough HCl such that all of this will be converted into that. So how do you do this? Well, you start with the amount of starting material, again, 1.5 grams of zinc. Quickly convert that to number of moles. You always want to move away from grams. Go to moles, that's where the comparison happens. So that's what we do. How do we do that? Well, we divide by mole mass. Okay? The molar mass of zinc is what you get from the periodic table. Then I have my quantity in the number of zinc atoms expressed in moles. And then I can see, okay, for each 1 zinc atom, I generate 1 zinc chloride compound. So it's 1 to 1. So that means I can convert from zinc to zinc chloride. 1, 1. But this doesn't have to be 1 to 1. I mean, you can have a chemical equation where this is 4 and this is 5. And then actually this is going to be 5 and this is 4. Right? And we'll see an example today of that. So now I have converted this quantity into the quantity, the number of zinc chloride units. And then now I want to convert that back to number of grams. So what I'm doing then, I'm going to multiply the number of zinc chloride units expressed in moles with the mole mass to find out how many grams of that stuff I have. Okay? In this case, you find 3.185 grams of zinc chloride. This is exactly the same calculation, just different names, but this is a general formula. There's 2 things you can do. You can try to put this in your head and memorize the method, and then try to recognize where you have to apply this. And then hopefully you're right when you do that. I'd rather have you not do that, because that's the kind of knowledge that dissipates like that. Okay? That means you do your exam and it's just completely gone. What I'd rather have is that you try to get a feel for this. Why do you do this calculation the way we do it? If you understand, you can reproduce that. You can explain to yourself why you do it this way. That's right. Okay? Even better, if you can explain it to your 4-year-old sister. That's even better. Okay. So let's move on to the following situation. We look at chemical equations. We can now calculate, given the amount of starting material, how much product we will generate. Okay? What we have not looked at is very important and very real situation. Namely, when does a reaction just stops? When does it really stop? And it does stop intuitively when one of the reactants runs out. Okay? So let's say if I have this candle here, which is a chemical reaction, this wax. The wax is being combusted, which means it reacts with oxygen. There it is. This is wax. Very nice hydrocarbon. And reacts with oxygen to produce again H2O and carbon dioxide. That's the combustion reaction. You see many of these now. Okay? When does this reaction stop? Well, it stops when one of the reactants is running out. Okay? So if I have no more wax of no more oxygen, the reaction can go on. That's when it stops. However, the question is, which of these reactants is running out first? Alright? Well, in case of this particular candle, or in general, if you light a candle, when does the candle stop? When the oxygen is burned out, or when the wax is gone? Yeah, typically when the wax is gone, right? Because there's so much oxygen, unless you put a glass thing around it, that's when you lose the oxygen. But if you just have it in the open air, there's so much oxygen around. This oxygen here is not the limiting factor in this combustion reaction. There's enough of it. Okay? When it comes to oxygen, this thing will go on forever. That's why if you have a forest fire, the forest fire will just go on. It won't stop because oxygen is running out. There's enough of it. So it's the other part that is the wax. Okay? So the wax in this thing is called the limiting reagent. And that is something we're going to talk about right now. So the limiting reagent is that reagent that is running out first, and hence will stop the reaction. And because it's running out first, it will also determine how much product you will form. Okay, so if you have to calculate how much CO2 you form, it doesn't make a lot of sense to look at how much oxygen you have in the beginning, because there's enough of it. It is determined by this guy. This guy is defining how much of this CO2 you form. The limiting reagent determines basically the number of molecules you produce. All right, so just to visualize that, okay, you have to make it simple for yourself. Here is a very simple chemical reaction. Namely, blue guy interacts with the red girl, and they form a couple. Okay? Now, let's say we have 3 blue boys and 4 red girls. How many couples can you make?
3.
Wow. That's right. 3 couples. 1, 2, 3. Well, I have also 1 red girl left. She can't find a partner. Very, very sad. So what is the limiting reagent?
The blue guy.
The blue guy is the limiting reagent. And the girls are in excess. They are in excess. There's too many girls. Okay? So we call the red girls here in this case the excess reagent. And the same holds for molecules, of course, right? It's exactly the same, there's absolutely no difference. And even these numbers, you think, oh, it's just like 3 or 4, that's easy. Hey, 3 or 4 moles, okay? Things like that are also easy. It's the same, there's no difference. Okay, so the limiting reagent is a reagent that runs out first, limits the amount of product you can form. Okay, this guy here, 1, 2, 3, determines how many couples you can make. The girls don't determine that, because there's enough. So this guy determines how many couples you can make. It defines how many molecules you form. The rest is in excess and is left over after the reaction has come to a stop. Okay, so after the reaction comes to a stop and you make the product, you have something else in the pot, and that is the excess reagent. And we are able to calculate how much we have left as well. We'll do that in the next couple of slides. Okay, now let's do a quick exercise here. Here's a chemical reaction. Nitrogen interacts with hydrogen gas to form ammonia molecules. Okay? So let's again do this in a visual way. Instead of having girls and boys, we have molecules now. For some people, this is too much of a hurdle to take. Okay? You replace boys and girls with the word molecule, and suddenly they don't understand anything anymore. Okay, so don't let it be you. Okay? It's really what I'm trying to do is show exactly the same thing. There's no difference. Molecules are the same as all of us. Here it is. 2 nitrogen molecules, 3 hydrogen molecules I have. Okay? This is my starting situation. How many of these guys can I form? Now, these guys are now composed of 1 nitrogen, so each of these molecules needs 1 nitrogen. It needs 3 hydrogens. Okay? I have 4 nitrogen atoms. I have 1, 2, 3, 4, 5, 6 hydrogens. 6 hydrogens means I can form 2 of these molecules, and then I'm running out of hydrogens. Okay? So what I can do is I can take 1, 2, 6, all 6, combine them with 2 nitrogen atoms, then I can make these 2 guys. Right? 1, 2, 3, 1, 2, 3, that's 6. 6 here, 1, 2 blue guys here. So, in other words, I have completed my reaction. I have 1 left. That is apparently the one that's in excess. So in the same kind of terminology as the previous slide, you can call this the limiting reagent. Hydrogen molecules are running out first. They determine how much of ammonia can form. And the other guy is the excess reagent, in this case, the nitrogen molecule. Okay, now, let's now look at questions like this. Let's determine what is the limiting reagent in this particular question. All right, so I have a mixture of magnesium and iodine gas. I have 5 grams of magnesium and I have 75 grams of iodine gas. And my product is called magnesium iodide. Identify the limiting reagent. Okay, so which one is running out first in this particular case? Now, if you look at the masses, you may argue, oh, look, I have 5 grams of magnesium and 75 of iodine. So this one must run out first because I have less of it. That is not how it works. Why not? You don't know how much this guy weighs. I mean, what if this guy, its mass, is 5 grams? Then he only 1. And what if this guy weighs like a fraction of that? Or vice versa. You don't really know how many of these magnesium atoms you have, or how many iodine molecules you have. So you really have to convert these numbers here to countable objects, numbers. Okay? So that's what we're going to do. Before I do that, I want to check very quickly, if I have 1 mole of magnesium, how many moles of this do I need to make a product? And that's called the mole ratio. Okay? These guys like to react 1 to 1. Right? 1 mole of magnesium and 1 mole of iodine gas will react 1 to 1 and will exactly form 1 mole of magnesium iodide. So if I have the exact same quantity, exact 1 mole of each, they run out at the same time. And there's no limiting reagent. They both are limiting. But if one of them is more or less, then you have a limiting reagent situation. Okay, so this is the mole ratio of the balanced equation. The balanced equation says these guys react 1 to 1. Now let's see what the actual mole ratio is. What is the actual mole ratio? It is how much you actually have. What I actually have is this and that. So I'm going to convert these numbers to number of moles. Okay? So 5 grams of magnesium, I'm going to convert it to a number of moles of magnesium. I do that by dividing by the molar mass. 24.3 is the molar mass of magnesium, and I find a total of 0.2 moles of magnesium. And I do the same for iodine. There it is, 75 grams of iodine. Now, note, this is iodine 2. So that means you multiply the molar mass of the iodine atom by 2, right? So 1 mole of iodine 2 is this much. Twice the molar mass of the iodine atom is the molar mass of iodine 2. And you find this much. So 0.269 moles of iodine 2. 96, thank you. And if you take the ratio of that, so I do exactly the same as here. 1 mole of magnesium, 1 mole of iodine. I have this many moles of magnesium and this many moles of iodine. That ratio is 0.697. So why do I do this? Well, this is more than that. Okay? Magnesium is on top, iodine at the bottom, magnesium on top, iodine at the bottom. It's less than this number. What does that mean? That means apparently I don't have enough magnesium to make this 1. Okay? If this number would be larger, I get close to 1, and it would be really large, it would be more than 1. So basically, if this is less than 1, that means that the numerator is the limiting reagent. I'm running out of magnesium first, because there's less of it. Yes?
Is it possible to tell the limiting reagent just by looking at the moles without doing?
You can, okay, this is a good question. But the question is, can you just look at the number of moles here and just decide which one is more? The answer is yes, you can do that if you have a reaction where it reacts 1 to 1. What if the reaction is not like that, but like 9 to 14? Then you have a harder time to figure it out. Yes?
So for reaction 1 to 1, the number I get corresponds to 21.
Yeah.
9 divided by 14. How would you know?
Okay, so let me continue the next slide and I'll tell you exactly this particular method. This is kind of like a method, and this is the method that always works, and you would be wise to apply it. There's more ways in which you can get to this answer. Okay? But let's see. What you want to do is this. Identify the mole ratio of the balanced equation. That was the 1 to 1 that we just identified. Those are the stoichiometric coefficients. It's the mole ratio between the reagents. Then we're going to calculate the mole ratio of the reagents in the actual number of moles that you have. We use quantities that are given in the question. Okay? We call that the actual mole ratio. And then you're going to compare the mole ratio as stipulated by the equation with the mole ratio that you get from the actual numbers of molecules that you have. And then you have two possibilities. Namely, if the actual mole ratio is smaller than the balanced mole ratio, then the numerator is the limiting reagent. So in the previous case, we found the balance was 1. This actual one was less than 1, which means the numerator is the limiting reagent. Okay? But you can also have the reverse situation. If the actual mole ratio is larger than the balanced mole ratio, then the denominator is the limiting reagent. Okay? So this is a kind of a simple, this is really a trick. I don't really like tricks, but in this particular case, it is a trick that will always get the right answer. So it's just a quick way to determine what do you have more of, basically. That's what it is. Okay, so what we have to do then in all these kind of exercises is to identify the mole ratio from the equation. The equation tells you what the proportion should be if they would react completely. And let's say you both quantities of the reagent are perfectly matched. In reality, this is typically not the case. We call that the actual mole ratio. Okay, so comparing the balanced mole ratio from the equation with the actual mole ratio you calculate will get you to determining which one of the reagents is the limiting reagent. Okay, now let's do a quick question because it's a lot of talk. Okay, I have a reaction of ammonia with oxygen. It forms nitrogen monoxide and water. So this is a reaction. And the question is, what mass of nitrogen monoxide is formed? So how much of the product am I formed? And, very important, how many grams of the excess reagent do we have left? Okay? So this is a question, very typical question. I have a reaction. There's a limiting reagent which defines how much product I form. And then also to calculate how much of the excess reagent do I have left after the reaction stops. There are two questions basically. Two questions in one. Okay, so the first thing you would like to do is to figure out what kind of chemical reaction am I talking about. So I have ammonia, I have oxygen. Those are the reagents, nitrogen monoxide, and water. Those are the products. So here is the balanced equation for you. Ammonia, oxygen, nitrogen monoxide, and water right there. It has the stoichiometric coefficients. Look, these are not 1, okay? 4, 5, 4, 6. So here we really have to take care of the ratios properly. Okay, so now we know the equation. Next, I would like to know which one of these two reagents, there's two, one of them is the limiting reagent. Okay, so let's do then what we just talked about. I'm going to calculate first the mole ratio between these two guys based on the equation. The equation says you need 4 moles of ammonia for each 5 moles of oxygen. And that is point A. Now, why would I put nitrogen on top and oxygen at the bottom? It doesn't matter. I can flip this over as well. Okay, I'm going to get oxygen on top and ammonia at the bottom. I would get a different number. That number has no particular meaning. It only has meaning relative to what I'm going to compare it with, which is the actual mole ratio. As long as you calculate the mole ratio for the balanced equation in the same way as the actual mole ratio, which means the same guy on top and the same guy at the bottom, you'll be fine. Okay, so it doesn't matter which one you put on top or the bottom, as long as you be consistent in your calculation. Okay, point A is the one we determined here. Now I'm going to determine what is the actual mole ratio. For that, I need these actual values. In grams, I see, but I don't need grams, I need moles. So I'm going to convert these 3 grams and 5 grams into moles by dividing these numbers by their respective molar masses. So there we go. I have 3 grams of ammonia. I like to convert it into number of moles, so I'm going to divide that by the molar mass of ammonia, which is 17 grams per mole. That calculation tells me 0.17 moles of ammonia. I have another reagent, that is oxygen. I have 5 grams of oxygen. Now, again, be careful here, this is O2. A lot of folks tend to forget that these are 2 oxygen atoms. So you have to multiply the molar mass of oxygen atoms with 2 to get to this molar mass. I divide this by the molar mass of oxygen 2, which is 32 grams. So I find 0.156 moles of oxygen molecules. Okay, so let's calculate the mole ratio. And I just have to be consistent relative to the previous mole ratio. I put NH3 on top and oxygen at the bottom. Same as what I did on the previous slide. And then I'm going to compare these two guys. This is 1.13. 1.13 is more than 0.8. If it's more, that means that the denominator is the limiting reagent. Okay? The limiting reagent is O2. That means that the other guy, ammonia, is the excess reagent. Okay? So you will have some ammonia left after the reaction stops. Oxygen is completely gone, all reacted, NH3, something's left. And we have to determine both. We have to determine how much product we form and how much of this stuff we have left after the reaction. Okay. So, let's move on and calculate how much product do we form. I need the amount of limiting reagent because the limiting reagent determines how much product I form. So what I'm going to do is, I'm going to say, look, I have 0.15 moles of oxygen. Oxygen is the limiting reagent. And that's the number I just calculated. Then, I would like to know, for each mole of oxygen, how many moles of nitrogen monoxide do I generate? In other words, what is the mole ratio between the two? So I'm going to convert the number of moles of oxygen into the number of moles of the product. How? By making the mole ratio between the two. 4 moles of the product for each 5 moles of oxygen. I make a ratio with oxygen at the bottom and nitrogen monoxide at the top because I want to go to nitrogen monoxide. Just like that. Moles of oxygen will strike out, and I'm converting this whole thing into moles of nitrogen monoxide, which is the number of moles of the product. Okay? I can immediately multiply that by the molar mass of nitrogen monoxide. So, this first part here is the number of moles of nitrogen monoxide. The last conversion is going from moles to grams by multiplying by the molar mass of nitrogen monoxide. This calculation tells me I have 3.75 grams of the product. You see, these calculations can be fairly quick. Okay, so that's the first part. The second part is, how much of the excess reagent do I have left? How do you do that? Well, what I want to know is how much has reacted, all right? And how much did I have initially? So I had a whole bunch of ammonia molecules in the beginning. Some of it has reacted, and the rest is what the excess is. So how do I determine what is the amount that has reacted? Well, that's determined again by how much limiting reagent you have. Okay? The limiting reagent determines how much stuff will react. So what I have to do then, I again start with the limiting reagent, the amount of it, 0.15 moles, and I have to convert this into the number of moles of the other reagent. How? With the mole ratio. Okay? For each 5 moles of oxygen, I have 4 moles of, or I need 4 moles of ammonia to react into 4 moles of nitrogen monoxide. So converting oxygen into ammonia involves this. Okay? 4 moles of ammonia for each 5 moles of oxygen. Moles of oxygen will cross out, and I convert this whole quantity here into moles of ammonia reactant. This is the amount of ammonia that has reacted in the reaction. Okay? That is a total of 0.125. So 0.125 moles of ammonia has reacted. After all the oxygen runs out, this is the amount of ammonia that came with it in reacting. The rest of the ammonia is still in the pot. So what do? Well, I take the amount that I had in the beginning, I calculated that on 2 slides back. I calculated that I had in the beginning, basically I have 3 grams of ammonia divided by mole mass was 0.17 moles, remember? So this is what I had at the beginning. This is the amount that has reacted and is gone. And so you subtract the amount that is gone from the amount that you had at the beginning, you get what you have left. And that is this much. 0.051 moles of ammonia. That is the amount in excess. All right, I'm almost there because they say how many grams. I have the amount of moles. I multiply it with the mole mass of ammonia, which is 70 grams per mole, and I find the answer. 0.869 grams of ammonia. Okay, so this is a little bit more involved because you have to realize that the amount of excess reagent, to determine that, you have to first calculate how much has reacted and subtract that from the amount that you had in the beginning. This may seem logical at this juncture, but I can tell you, honestly, about half of the people on the exam will do this wrong. Okay? About half of the people will do this wrong. They think that the amount of excess reagent is simply either this or that. It's not. Okay? Think of it as the boys and girls that we had in the beginning. Everybody saw it directly, I have just one girl left. Okay? Because you subtract 3, which is reactive, from 4. You have 4 in the beginning, 3 as reactive, you have 1 left. It's the same thing. Exactly the same thing. Don't be mistaken. Okay? Every year, 50% of you guys will not do this correctly. Just forget the last step, subtracting or, yes?
On the first slide of this example, the equation wasn't given, but here you give it.
Yeah?
Will we be given that on the exam?
Well, I mean, depends on the kind of equation. If the equation is simple enough that you can balance it yourself, that could be, also the first part of the question could be balance this equation, for instance. Okay? And then you can continue the calculation with the mole ratio and so forth. So yes, you should be able to balance simple equations. It's part of the maturity.
Let's say like how you given ammonia example, and if you didn't give the balance equation, would be expected to know right off the
Okay. The question, I think the question is, do I have to know what ammonia is? Is that the
Yeah, not
question?
necessarily ammonia, but whatever you use for
Okay, so I think I know what you mean. If I write in words the chemicals, do I have to know what they are? The answer is yes. I will only write down the chemicals that you should know, and not some kind of exotic things you've never heard of, because that would be ridiculous. Right? Okay, another one. This is the same kind of calculation with slightly different content here. So again, don't be flustered when things slightly change. Okay? Let's have a look. This is exactly the same question, slightly different formulation. I get a reaction. In this case, dinitrogen pentoxide crystals, and they react with water, and they form aqueous nitric acid. The question is, what is the reagent, and what is the mass of the product? Okay? What is different in this particular question is, one of the reactants, the mass is given. The other reactant is actually water, which is a solvent too. Okay, so water is the one that's reacting and is a solvent at the same time. You have 2 liters of it, and there's no mass there. But there is a density given. So from the density you can calculate the mass, and from the mass you can calculate the moles, by dividing by the mole mass. Okay, so that's really what you have to do. But if things are slightly different, don't be kind of like confused. This is the same kind of question. All the information is there. Okay, first things first, I'd like to see what is the chemical reaction here. Dinitrogen pentoxide, that is a compound you should be able to write down. Okay? There it is. Dinitrogen pentoxide, it's 5 oxygens and 2 nitrogens, plus water. And look at the physical states I have to put there. Okay? Solid and liquid. And this is my product. And that is dissolved in the aqueous phase. Okay. I have to be sure that this one is balanced. Let's quickly check if that is true. I have twice, that's 6 oxygens. I have 1 here, 5 there, that's 6, 2 nitrogens, 2 nitrogens. Okay, this one is balanced, so I'm fine. Second, I have to determine the limiting reagent, and I start by looking at the equation itself and look at the mole ratio. Okay, so I see that I have, for each 1 mole of this guy, I have 1 mole of water that I need to completely react. So the reaction is 1 to 1 because the stoichiometric coefficients are 1. All right, so the next step is to compare that with the actual mole ratio. I have the mass here. I can divide this mass by the molar mass of the nitrogen pentoxide, and I use this information here, the liters and the density, to calculate the number of moles of water. Now, intuitively, you already know which one is the limiting reagent. Would it be water, or would it be the other guy? it's most likely the other guy. If you have a bucket of water with 2 liters, okay, that's a lot. It's a lot of water. So most likely it is the dinitrogen pentoxide that is the molecule that's going out first. But you have to double check. But it always helps to kind of look at the question and kind of like try to understand what is the scope here. Okay, what is probably the right answer. Okay, so I'm going to take this. This is 540 grams, and I'm going to divide that by the molar mass. So converting kilograms to grams. So I like to have 8 grams. Okay, 1,000 grams over kilogram. Then divide by the molar mass. 108 for dinitrogen pentoxide. And I find the number of moles, which happens to be 5.0. It's a nice number. All right. Next step, let's do the same for water. There it is. 2 liters of water, I have to go to a mass. Unfortunately, the density is given here, okay, in grams per milliliter. So what I do first, I'm going to convert this to milliliters. There's 1,000 milliliters in 1 liter. That means I have 2,000 milliliters. 2 liters equals 2,000 milliliters. And then I can multiply it by the density here, 1 gram per milliliter. There you go, 1 gram per 1 milliliter. So that means now I have my number of water molecules expressed in grams. In order to get the moles, I have to divide by the mole mass. And the mole mass of water is 18 grams per mole. So this calculation here should give me the number of moles of water. 110 moles of H2O. By the way, only one significant figure here, but I'm going to assume for all intents and purposes in this case that this is infinitely precise. Okay? It's not really nicely phrased in this question, I must admit. So it's not a limiting step in the calculation. I'm going to assume. Okay, so I have to kind of compare these 2 guys. Look at the ratio. There it is. Reagent number 1, reagent number 2, the ratio equals 0.045. That is much, much less than 1. That means the numerator is the limiting reagent. That is this guy. And my prediction was correct. I expected that water was not the limiting reagent. It was the other guy, dinitrogen pentoxide. Okay, so I take the number of moles of this to determine how much product I form. I'm going to start my calculation by writing down the number of moles of dinitrogen pentoxide. I have 5 moles. I want to convert that into the number of moles of the product. Okay? For each 1 mole of dinitrogen pentoxide, I generate 2 moles of nitric acid. Nitric acid goes on top, this guy goes at the bottom. Okay? So this will strike out, and effectively I multiply by 2. 2 moles for each 1 mole of this. And that's a total of 10 moles of dinitrogen pentoxide. 10 moles times the molar mass of, this is nitric acid, times the molar mass of nitric acid gives you the amount of grams of nitric acid. Same steps as we took before. From moles of one compound to moles of another compound through the mole ratio, multiplying by the molar mass of your final compound. In this case, the answer is 630 grams of nitric acid. So in this case, that's the end of this question. Okay, so recognize the flow in these kind of calculations. Okay, you do the same thing over and over again. Be sure you can make these conversions. All right. Last topic is this. Let's go back to one of our favorite compounds, which is this fellow over here, this beautiful orange ammonium dichromate. Let's assume that I have 1 mole at the beginning of my compound. And let's say I give you this compound, and I say, let's synthesize this guy, chromium-3 oxide. And you go to the lab, you do your best, you put your gloves on, your goggles, work the whole day, and at the end of the day, you say, look, this is what I get. I get my beautiful chromium free oxide. I get 0.8 moles. All right? And I say, hold on a second, what's going on? I gave you 1 mole of this. You don't generate 0.8 mole of that. 1 mole of this should be given 1 mole of that. The ratio should be 1 to 1. Well, you say, boy, that's all good and well, but I mean, I can't even perfect. There's an experimental error. I can make mistakes. So stuff goes, fly out of my bottle. I drink a little bit in between. All kinds of things can happen. So, in reality, this is what I really get. 1 is the theoretical yield, but the actual yield is less than what I theoretically can get. And that is very, very real-life situation. Right? This happens in the lab all the time. So, the percent yield is the quantifier for that. It says the actual yield divided by the theoretical yield times 100. So in this particular case, the actual yield was 0.8 moles. The theoretical yield said you should have 1. And if you multiply that by 100%, you get 80%. So in this case, you did a pretty good job. You got a percent yield of 80%, which is very decent for an aspiring chemist. So we have to be able to do a couple of calculations with percent yield. And this is all there is to it, really. This is the definition of percent yield. So let's do one quick calculation to implement. Here it is. It's a reaction, of course. Calcium hydride is going to react with water. Look, in excess. That's great. The question already tells me which one is in excess and which one is a limited reagent. I don't have to determine that in this particular case. And the product is calcium hydroxide precipitate, and the other product is hydrogen gas. It also says, look, the yield is 84.3. Now, given this yield, what is the mass of calcium hydroxide that you synthesized? All right, let's do this. First, and this is always the first step, I want to know what is the reaction that we are talking about. Calcium hydride is this compound right here. Calcium with 2 hydrogen atoms. Calcium 2 plus and hydride is H minus. 2 of those will give you a neutral compound. It's solid because that's what the question says, so don't forget the state of the material. Water is liquid, so I put L there. And this is the product, calcium precipitate, calcium hydroxide. And this is hydrogen gas. The reaction is already balanced. You can quickly see that. The number of hydrogens is balanced on both sides. Okay, so let's assume that the yield is 100%. How much would I generate? Well, if you want to calculate how much you generate, you have to first know the limiting reagent, and then convert the limiting reagent into moles of limiting reagent, then into moles of the product, and then from moles of the product into grams of the product. Right? So let's do that. Limiting reagent is given. It is calcium hydride. I have in the beginning 3.74 grams. I have to convert that, as before, in moles. Okay? By dividing by the molar mass. 42.1 is the molar mass of calcium hydride. Okay, next, I want to see how much product I form by looking at the mole ratio of the reactant with the product. That is 1 to 1. Each 1 mole of calcium hydride will generate 1 mole of calcium hydroxide. Okay, so this whole thing here is now number of moles of calcium hydroxide. And I can now calculate the number of calcium hydroxide, the quantity of calcium hydroxide excess in grams. Okay, and multiplying by the molar mass. So I do the same conversions as before. A total of 6.58 grams of calcium hydroxide. So what is the next step I have to do? Let's have a quick look again at the question. The question says, what is the mass of calcium hydroxide that you would form, in this case, given that you have a yield of 84%? This is what I have, what I would have gotten if I have 100%. I don't have 100%. I have less. I have 84%. So what I have to do, really, is to take 84% of this. So the actual yield is 84% extract its fraction, which is 0.843 times the mass, which this is basically the theoretical yield. Okay, this is the theoretical yield. This is the actual yield, and this is the percentage expressed in the fraction. So I can rearrange the formula of percent yield. Theoretical yield. This is the reaction yield, and this is the actual number that you get in terms of grams. So if you multiply these two numbers, you find 5.55, and that is the actual amount that you made. Now, there will not be a lot of questions on the homework. Homework 6, 1% yield, but there will be a whole bunch of questions about implementation and stoichiometric calculations. So please get busy.